Welcome guys in another video of Unico Dev. Today I'm going to be showing you something I've been creating for a while now. I mean, it's been a few days, and this is all the code. It's not that much, okay? It's just like almost exactly 200 lines. Actually, let's do this. This is an application, okay? An Android application for your phone, and basically I'm going to show you what it does. Probably you already know from the title of this video, but I'm going to show you. So, I don't, oh my gosh, I messed it up. Okay, so basically, I'm too lazy to, like, take the phone out and, use a recorder for the phone. So I just created a little bit of I just took a simulator for the phone. So imagine this is a phone, okay? This is a phone application. So basically what this is gonna do, it's gonna get the parents' genotypes, okay? And it's gonna give you all of the son's information. Now, you may say, Nico, what is this? I don't know anything about this. If you want to know more about what this is, I suggest watching like a genetic video, like the basics of genetics or Mendel laws. If you don't know what those things are, you're probably gonna learn at school anyway. But I suggest you watching some videos about that before watching this video. I'm gonna leave some content in the description for you to enjoy. And now let's crack on and see how I did this. So basically, let's pretend we have a parent. Okay, what we can do, okay, let's pretend that we have a plant, okay, with green seeds. So this means that both of the alleles, well, but basically it means that both of the letters are capital G. G stands for green. But basically, if you don't know anything about genetics, the main thing that you need to know is that a gene in a parent genotype, that is this one, appears twice. And I just closed the app. I'm really amazing at my job. Okay, appears twice, okay? So, an example, for the color of the seed, there can be two states, either green or yellow, an example. Now, you must distinct the two different states because one of them is dominant and the other one is not. Now, we're gonna see what that means, but basically I'm gonna indicate a dominant state as a capital, G, and G stands for green, and that is not a capital G, that's a F. Okay, a capital G, and the other one I'm gonna indicate it as a normal G. Now, if a parent is pure, it means that both of the letters, both of the alleles, or whatever that is pronounced, are both of the same letter. So we have capital G, because, it's green, and if we do lowercase gg, then that means that it's pure yellow. So I'm gonna say it once again. Capital G, pure green. Not capital G, lowercase g means pure yellow. Now what we're gonna do, we're gonna put together pure yellows with pure greens. So this is gonna be pure green and this is gonna be pure yellow. And thanks to my application, if we calculate, it's gonna tell us all of the information about the songs. So basically what it's gonna do is gonna first, take both of the genes, so like the one G and the other G is gonna tear them apart, and it's gonna do it for the first parent and the second parent, and then basically it's gonna do every single combination of those. So as you can see, look at my mouse right now. The first G is gonna go to the second one, and the same one is gonna go to this one. Then this G is gonna go to this one, then this G is gonna go to this one. So we're basically doing every single, combination of both of the parents that create the sounds. And as you can see, capital G, lowercase g, uppercase G, lowercase g. Every single combination is gonna do always the same result. That is uppercase G, lowercase g. So as you can see, all of the sound combination, as my algorithm suggests, are the same. So the genotypes of all the children are the same, and the genotypes are capital G and G. Now, since G, capital G, is dominant, this means that the phenotype, aka what we actually see, is gonna be G. So, if you take a pure green seed parent for a plant, and you take a pure yellow seed parent, and you mix the DNA up, the children that will come will all be green, because green is dominant over yellow. Now, I hope I was clear, but this basically is the first law of Mendel. Now, I'm not the best to explain this kind of stuff. I'm studying it at school right now too. I thought that I'm gonna leave some content below that you guys can see and enjoy if you wanna, learn more about this awesome stuff. The fun thing though is that my algorithm works, and that's actually something amazing because my algorithms never work, and this took a while to perfection. Now, we're gonna try to do something even crazier. Instead of doing only one gene at a time, we're gonna do multiple. So we're gonna do like GG, BB, and here we can put something like this. Can be whatever you want. Then we can do FF, and here we can do both capital Fs, and then we can do SS, and this can be S... No, let's do both capital S. So you can do whatever you want, and then it's gonna calculate, it's gonna take a while, and it's gonna do every single combination. Now, the combinations are gonna exponentially get higher. But as you can see, oh, look at that, we got a really lucky combination. Look at that, all of the sounds, are they all the same? Okay, so now let's try something else, okay? So we know that this is gonna retrieve us 4 different children that are all the same. Now the problem is that the children that we get, they are not pure, okay? Because the parent was a pure green, and a pure capital G, and instead, the other parent was a pure normal G, so a pure yellow. But the son that we got actually are not pure. They are called hybrids, because they have a capital G and a non-capital G. So what does that mean? Well, their phenotype is always green, because green is dominant, we already said that, so it's always capital G. But this means that if we, mix their DNA together, so now we're gonna, take 2 of the sons and mix their DNA together, and we calculate, we're gonna get something completely different. In fact, we're gonna get every single combination possible, all of the 4 combinations of things. Look at this. Capital G goes with capital G and gets this thing, then capital G goes to this one and gets this hybrid, and then non-capital G goes to capital G and gets this other hybrid, and now capital G and non-capital G goes to the other non-capital G and gets this other pure. So now what we basically get is 1 pure green, 2 hybrids, and 1 pure yellow. And this is the second law of Mendel. So, this is pretty cool. We're like going through all of the laws together with my application that I'm gonna show you how it works in just a sec with all of the code behind it. I coded it in Java. I could actually do this as a computer application. Probably I'm gonna try to put it in as a computer application. I used Android Studio because I wanted to do it as an application, a mobile application. Now we're gonna try one last thing, and we're gonna explain, improve the third law of Mendel, and we're gonna try to do AABB and AABB. So basically the third law of Mendel says that doesn't matter how many, oh my gosh, why doesn't this work? Doesn't matter how many genes you put together. So first we only tried with 1 gene, okay? So, and we get this result. If we do more genes at the same time, Mendel basically says everything is gonna be the same. So genes are independent from each other. And that's what basically works. If you see at the result, as you can see, everything is the same, and we get the same sons, the same children. And as you can see, if we do only AA, we are gonna get children capital A, and if we add the B and do only B, we're gonna get capital B children. So if we put those together, naturally we're gonna get AB, as you can see. So yeah, it works. The third Mendel law is proved, and all of the 3 Mendel laws are proved. So that's amazing, my application works. That's a proof to show that my application basically works. It basically can take any genotype from the parent and return the children genotypes and phenotypes. So that's amazing. Now the only complicated part is like the start. That may seem pretty easy. Now the most complicated part, the part that I struggled most on doing was this. Dividing the genes. So, as you can see, we have capital A, capital B, and we have to divide it in this kind of way. So basically what we have to do is this A must, mix with this one, and this A must be mixed with this one. So they are all, have to be 4 combinations possible. Now, how did I do this? It was really complicated. So basically what I did, since I wanted to get every single combination possible, I had to think of a way to retrieve all of that information, And I actually got a really interesting way to do it. I did it here with my code. I'm gonna show you. So basically, we have this variable that is called binary composition. Basically, what it's gonna do is gonna get every single binary number from 0 to a certain limit, okay? And this binary number is gonna basically tell us if we need to get the first letter or the second letter of each gene. So basically, let's run this through, okay? Let's pretend we are at the first combination, okay? We have 0, 0 as a binary number. So 0, 0 naturally is 0 anywhere. So this means that we get the first letter, the letter A. We're gonna do another combination because this may be a little bit more trivial. So we're gonna do something like this, okay? So 0, 0 means that we get the first letter, the capital A, and the second letter, the third one, the capital B. So we always get the first letter of each gene. But instead, if, the binary composition is 0, 1, it means that we get the first letter, capital A, from the first gene, but the second letter from the second gene. So we're gonna get lowercase b. And if we go forward with binary numbers, it turns out you actually do every single combination. So basically what I did, I made this array that is full of binary numbers, and then I just run this math through, and I do every single combination, and then I print the combinations here in this text view. So that's all there is to it, and it's like the simplest thing ever. So what's next? Now I have to mix the genes up with both of the parents. So basically what I have to do is what we did before. This AB has to go here, 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 here. This other one must go here, 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 here. Third one, all of these. Fourth one, all of these. So each one must combine with the other ones. It was really simple. In any coding language there are loops, and you can just put a loop inside a loop, and you can basically do that with normal, math. So it's something pretty simple. Where did I do it? I forgot. Oh, here you go. So this is the code that basically makes it. So it takes, it sums the genes, but it does that for every single combination, because, we have two loops. One for the first array of genes, and the second for the second array of genes. So this is pretty simple too. Now the third part, the third phase, that is actually pretty hard, is sorting all of the arrays up. Because basically what we're doing, these are strings, by the way, and we're basically summing them. So we have like AB, and we sum it to AB. So what we would get, if I didn't do this algorithm too well, we would get AB, AB. But that's not what we want, because we want them a little bit more sorted. We want the A's before the B's. I don't know if I make sense. If this wasn't sorted, here I would get something like AB, AB. Instead, I get the A's before the B. So that is basically what that is. And so basically that algorithm that sorts the letters out is done here. It's something pretty trivial, actually. It basically will detect if a certain letter is capital, and if it's capital, it's gonna put it before the non-capital one, because that's the official genetic notation, and I have to respect that. So I have to do this little algorithm. It's nothing really too crazy. It's just a sorting random algorithm that I came up with. So nothing really. Now the last part is actually getting from the genotypes of the children to the phenotypes of the children, and that's also pretty easy. As we know, if we have an hybrid, meaning we have an impure gene, meaning we have capital A and lowercase a, an example, we can simply say that the phenotype, so basically what we're gonna see, is gonna be capital A, because A is dominant. So I just had to do a little bit of an algorithm, and it's this one. Pretty simple. It will just detect if in the code there is a capital letter, and if it is, it's gonna put it in the phenotype. It's a little bit basic. But anyways, yeah, this is how the entire code works. It's gonna be on GitHub, and so you can check out the source code. You can even add more stuff, and do pull requests, and I'm gonna accept them. You can fix bugs. There are not any bugs. I actually worked a lot to fix every single bug. As you can see, oh my gosh, no, don't delete the code. Oh my gosh. Okay, so as you can see, if we go here and we delete this and we delete this, if we leave them both empty, it's gonna basically say genotype fields are empty. And if we say something that is not a genotype, it's gonna say invalid. And also, if we say something that is a genotype, so AA, BB, CC, but here we don't put the matching letters, we do something like DD, HH, JJ, then if we calculate, it's gonna say that they're not compatible. So, it works like a charm. Also, there is also one last thing. If you do something like this and then you add DD, it's gonna still say that they're not compatible, because they need to have the same length too. So as you can see, something like this is not compatible. Well, this is invalid, but still, you get the point. But yeah, this is what I wanted to show you. I'm really excited about this, and I want to learn more about genetics, and try to do different calculators. So basically, this is a calculator that gets from the parents to the children. I would like to do something opposite, so like get from the children to the parents, or basically work on some special cases, like codominance or incomplete dominance. I still have to add those in. And if you want to know more about this algorithm and calculator, as I said, everything is going to be in the description. There is also going to be an APK, so you can download this application for yourself, and you can like cheat in science tests or something like that. It's going to be amazing. If you cheat on a science test, you have to pay me $2, because that's how it works. I'm just kidding, you don't, but please don't cheat. Anyways, that was it for today's video. Hope you really enjoyed it. Hope you really enjoyed this little, can we call it like a tutorial? I don't know. But yeah, I hope you enjoyed what I've been up to. And this code, if you want to check it out, as I said, if you want to see how it works, everything is in the description. Go check it out and have fun.